Let's give a high-level explanation of transformer architecture, and specifically we're going to focus on the decoder for this video, not the encoder, since that's what GPT uses. So why don't we just start with the embedding layers. So we're going to actually have two embedding layers. One of them is called the token embedding layer, and the other is called the positional embedding layer. So we'll discuss this one over here. And the goal of these embedding layers is actually to learn or train feature vectors. Specifically for the token embedding layer, the goal is to learn or train a feature vector for every single token in our vocabulary. So let's say we are doing a word level language model. So we can think of this embedding layer as actually a lookup table, and that lookup table will be of size, vocab size, where vocab size is actually the number of different words that this model can recognize. So maybe the total number of unique words in our body of text that we're training the model on. Vocab size by embedding dim, where embedding dim is actually our choice. And the higher that we make embedding dim, the more complex of a relationship the model can learn. Next is the positional embedding. So this is also another lookup table, except this one is actually going to be context length by embedding dim. You may have heard of context length discussed in the context of large language models. You might know that ChatGPT has a context length of 128,000, specifically GPT-4. And context length is essentially how many tokens back. So when you're talking to these language models, how many tokens back in the sequence can the model read? Because at some point, it has to essentially cut off and say, okay, the model's not going to factor in anything that was this far back. But how far back can the model actually read? That is the context length. And similarly, during training, when we are feeding in batches and batches of training examples, we will actually be feeding in B by T tensors, where B is the batch size and T is the length of each, say, sentence in this training batch, and T will actually be the context length during training. So the positional embedding is essentially another lookup table that has context length rows in it. So this would be from 0 to context length -1 in terms of the rows or indices of that table. And the number of columns or the size of each row is also the embedding dimension, where we are essentially going to learn a vector of size embedding dim for every single possible position. So what are we actually passing in to the positional embedding layer? Because we know for the token embedding layer, we're literally just going to pass in the input tokens themselves, and the embedding layer here is actually going to then look up the feature vector for each token, because we have vocab size number of rows, where each row corresponds to a token in our vocabulary. However, if the rows here are going from 0 to context length -1, then that's actually corresponding to positions or indices in a sequence. If we send in write me a poem, we would say that write is at position 0, me is at position 1, a is at position 2, and so on. So to pass in, what are we going to pass into the forward method for the positional embedding layer? We're actually going to pass in the following, torch.arrange of capital T, where torch.arrange actually generates a tensor of size T that is sorted in order, where its values go from 0 to capital T -1. And that's how we would essentially want to index our embedding lookup table. And once we have the token embeddings generated, once we have the positional embeddings generated, we simply go ahead and add them in. We just add those two tensors together before we'd feed them in to the transformer block. Next is the transformer block. Once we have actually added our two embeddings together, the token and position embeddings, we're going to go ahead and pass that in to the transformer block, this gray rectangular box over here. And this part actually does the heavy lifting within a transformer. This is what allows the model to predict the next token in the sequence so well. And the most important parts of the transformer block, we won't go super in depth about this entire box over here. I actually got a separate video on that, but we will kind of give a high level explanation for what it's doing and how to code it up. So the most important part is probably the masked multi-headed attention. And that might sound like a mouthful, but this is essentially the communication part of a transformer. Communication. We know that we pass in sequences of words into transformers. So let's say we passed in write me a poem. At some point, the model needs to actually realize which parts of this sequence of words to pay attention to. and specifically which pairs of tokens are more important. So in the attention layer, the model will actually consider every single pair of tokens. This pair, this pair, this pair, and actually every single pair of tokens in any sequence, and the model will figure out which pairs of tokens are actually relevant to each other. So we know that write and poem must be relevant to each other, because how else would the model actually know what to write? The model shouldn't write a book, the model shouldn't write a movie, rather the model needs to know that a poem needs to be written. So the model will actually let these tokens talk to each other, so to speak. The model will consider every single pair of tokens until the importance of every token pair relationship is determined, and then the model can focus on certain parts of the input and appropriately predict the next token in the sequence. The other most important part of the transformer block is the feed forward component. And the feed forward component is actually just a bunch of linear layers kind of stacked together, as well as nonlinearities like the ReLU function. And if attention is communication, we can actually say that the feed forward part, or vanilla neural network part, is computation. The model is going to learn a ton of weights and biases, similar to a linear regression, in order to encapsulate the entire relationship between all of the words in the input so that the model can appropriately predict the next token. So that's the transformer block. It does the heavy lifting within the transformer. However, if you were coding up the GPT class, let's say we are coding up a class called GPT, you'll actually be given the transformer block class, and you can treat the transformer block class as a black box. However, when you actually are coding up the full transformer in the GPT class, you're going to actually notice this NX in the diagram. And that actually indicates that we're going to have many blocks in sequence. So what actually occurs in a transformer is the output of the transformer block. So the output over here is actually passed back in to the transformer block n number of times, where n is essentially the number of transformer blocks, and this is predetermined beforehand. Obviously, as we increase the number of blocks, the model gets more and more complex, and the model can learn a more and more complex relationship with more parameters. But to actually implement this into code, we're actually going to use something called nn.sequential. So in your GPT class, in the constructor, you will define something called nn.sequential. And you can actually treat this just like a Python list. You can call .append on an nn.sequential with the only restriction that the only thing this list can contain is other neural network layers. And then, once you actually call the forward method of the nn.sequential object, once you call the forward method of this object, it will actually call the forward method of every single block that was passed in to this list in order from left to right. So that entire process of passing in the output of one transformer block all the way back in would be handled by that line of code, and you will find that incredibly useful if you're ever coding up the GPT class. One additional component that's actually not included in this original famous transformer architecture is that in GPTs, something that has been found to work really well is after the last transformer block. So right here, an additional layer norm is used. So that's an additional nn.layer norm. And we know roughly at a high level the benefits of a layer norm by actually making sure that our data is centered around the mean and has an appropriate standard deviation. We find that we don't have such crazy extreme range of values in our neural network, and the training process is actually much smoother. So we're actually going to have one additional layer norm before the linear layer and the softmax layer. And the linear layer is something that we can actually think of as a vocabulary projection layer, because the dimensions for that linear layer, it will actually have vocab size. It will have vocab size neurons in that layer. So out features for that linear layer would be vocab size. And that's because the model needs to figure out what the next token is, and it's going to output a bunch of probabilities, specifically vocab size number of probabilities, as we will have a probability for every single token in our vocabulary, as every single token in the vocabulary could technically come next. And of course, last we will have the softmax layer. We will have a softmax layer over here, which will squash all our values to be between 0 and 1, so that we have a true probability distribution. Next, I would highly recommend jumping into the code and coding up the GPT class. Your job will be to write the constructor or init, as well as the forward method. And once this is done, you could actually train this GPT and then go ahead and use it for text generation. So I highly recommend jumping into the code.